Okay, welcome back to the next lecture of the week. This should be pretty short, depending on how long I want to spend on these examples. I only have 3 algorithms to show you, but they are quite fancy. So let's pick up where we left off. We talked about the traveling salesperson problem, where you have a graph and it's weighted, and you want to find a nice cycle so that you aren't spending any more gas than you need to because all the weights are like distances, okay? So you want to find the shortest possible distance for your path, visiting every possible city, coming back to your initial spot, and yeah, that's the shortest possible one there. Now it's time to program with graphs, okay? So a lot of the time we make graphs, and we want to like visit every vertex or like search for one vertex starting from another. Like we have graphs that represent our roads, and so like if I want to know how to get to San Francisco, maybe it's going to tell me to go take the 99 to the 150 whatever and transfer and things like that, and it knows the distances, and so that's how it like can calculate the time, okay? Things like that. So it's very nice to be able to search for things through a graph and also visit places, okay? So yeah, the idea is maybe like you're stuck in a maze and you have no idea how to get out, and one way to do it is to traverse the graph and visit every vertex, because eventually you'll find the end. It's like the trick of always stay to the right wall. Eventually you're going to get out of the like corn maze or whatever. That's the trick. So yeah, this is technically a graph, and we can visit every node. Like here is like the start, here is like the end, and here's how like they're all connected. You like use grids. So there's edges like this, like this, like this. See that? And eventually, that's supposed to be right there, you can see if you try all the ways of doing things. I won't draw everything. Like imagine that there's more over there and over there. Eventually you'll find the way to get out, because you're going to search for all the places and end up in plenty of dead ends. But eventually you will find a path of nodes, not that way, that gets you towards your end goal, okay? It looks like it's a very long path here towards the end. But you gotta try everybody. You gotta see which way is gonna get you to the answer, okay? So that is how this is a graph, in case you were wondering. So yeah, I'm going to show you all the algorithms now that traverse these graphs, and we'll talk about a bit more of of the theory behind these traversals in the trees chapter, which is next. Okay, so the first way to visit every node in a graph is to do it depth first, we say. Okay, DFS for short. This is a way of traversing every node in the graph, every vertex, and depth means we want to try and get as deep into the graph as possible before we change course. Okay, that's the idea. Go as far as possible without having to retrace our steps, and the time complexity is actually quite nice. It's linear in either the edges or the vertices, whichever one is bigger. So that's how this is going to end up working. Like if there's more vertices than edges, then V is going to win out in this addition, or if there's more edges than vertices, then E is going to win out in this addition. So usually it's E, but we say V plus E just to be cool and cover all our bases. So here's the algorithm right here. Here's how you do a depth first search. It's a long word. A depth first search in a graph, and you have to have a starting node. Okay, so there's always a starting vertex, and let's pretend that our starting vertex is A. Okay, so I'm going to, thank you past me, I'm going to number the order in which we visit these nodes. So here's what's going to happen. The way that depth first search works, and the reason why it goes deep into the graph, is because it's using a stack data structure underneath everything. Okay, it's keeping a set of visited vertices, and it's also keeping a stack to figure out which vertex to visit next. Okay, so normally when you have a stack and you push things to it, like you push A, you push B, you push C, and then you pop them off. You can draw it like that, but I'm going to draw it sideways, like this, A, B, C, then you pop them off in that order, okay? That's just so I can do it horizontally. Okay, so this is depth first search. It allows you to visit every vertex in a graph from a starting vertex. Okay, so here's what you do, assuming the graph is connected, that is. So start out your visited set as empty. So it begins being empty. And then you make an empty stack. That's going to tell you where to go next. And then you're going to push your starting vertex, the one that you want to visit first, and just like branch out from there. You're going to push that to this stack. Call it S. Okay, so the very first thing that goes inside of this stack is the vertex that we're starting with. And let's pretend, for this example, that it's A. So the stack looks like this when we're right here before we execute the while loop the first time. Okay, so here is what we do. Now it's time for the while loop to happen. And it's going to do something. It's going to take something out of the stack as long as the stack is not empty. And sure enough, it isn't yet empty. Okay, so the very first thing we'll do is pop the stack. So now we have A. Okay, we're going to take the A out, like pop it. Now we have A over here. Okay, we're calling it V up here. V is currently A. Yeah. So we've popped out the A, and then we are going to, only if we haven't yet visited A, then we haven't, because it's not in the visited set, we're going to visit it, whatever that means for our program. Maybe it's like print it out, maybe it's like, I don't know, spend a lot of money, who knows, just process this vertex in some way, and this is actually the whole point of doing a search. You want to visit all the places and do something with them, okay? So that's what visit like encompasses. And then, after we visited A, we're going to change our visited set to be whatever it was, union, I guess the set with that vertex. That would be more correct. Yeah? So now, visited holds A. All right, so the stack now has nothing because we popped it out. I'm going to leave it there, though, and the visited set has A. Okay, so now we're done with one, or almost done with one execution of the while loop. The last thing that we need to do is push all of these adjacent vertices to S. Okay, so A got visited first. All right, so it's number one. And then we're going to push all of these adjacent vertices. Let's just pretend we're doing it in alphabetical order. This is how we visit everybody. We're going to push B, C, and E into the stack in that order. Okay, so we're going to push B, C, and E to the stack. So now the top of the stack is, well, I guess it's E. That works. That works for me. Okay, so are you ready? Now we do the whole thing all over again. I'll show you why this is a bit of a waste in a little bit. It should become apparent. So now we're back at this loop. Well, stack's not empty. It's got 3 things in it now. Let us pop stuff from it. Okay, so we are going to, well, we're going to pop E. E is now our V. Okay, so we're looking at E, and we just, if we haven't visited it, we have not, we're going to visit it. Okay, so we have just visited E, and we'll add it to our visited set. So there goes E, and I'll just leave this empty without this for now because I'm going to have to keep erasing it anyway. So we've just visited E, that's the second thing we visited. And then we push all of E's adjacent vertices to our stack. And this is, again, how we're going to find everybody. Okay, so the adjacent vertices to E are A and F, and I guess I'll push them in alphabetical order. We're going to do A and F. Okay, so this is why it's a waste, because we might have to, or we're going to have to visit A again, even though it's already in the visited set, and we'll skip it. Okay, so that's what our stack looks like, and that's what our visited set looks like. So then we pop the next thing off the top of the stack. Maybe I should be redrawing this, because the stack, it looks a bit weird right now. Okay, so right now is BCAF. BCAF, that's what the stack really looks like. Maybe I'll just redraw it. BCAF. Okay, so then we take out F. That's the next thing that we process. So now F, F is V. pop. We haven't visited F yet, so we're going to add it to our visited set after visiting it. And then we're going to push all of its adjacent vertices. Okay? Push all of F's adjacent vertices. And because we visited it third, I'm going to write a 3 there. And so the adjacent vertices for F are B and E. So I'll push them in that order. B, E, just like that. Okay? So I can go a bit faster now because I think you're getting the hang of it. The stack's not empty. E is on the top. Pop it. Pop it, take it off. So now we're looking at E, and oh man, E was invisited. So we're not actually going to execute any of this loop. We're just going to be like done with it. So we pop off E, do nothing with it because we've already visited it. See that? That's the beauty of it. So now our stack looks like this. It's B, C, A, B, and now B's on top. It's not empty. So we're going to take out the B, and that's what we haven't visited yet. So it's not been visited, add it, visit it, add it to our visited set. It's the fourth thing we've seen, okay? And then we're going to push all of its adjacent vertices to our stack. And B's adjacent vertices are A, D, and F. Okay, so I'm going to push A, D, and F to the stack. Okay? That is the idea. And so it's trying to go as deep into like this path as it can, and it's eventually going to get there. Okay? So the next thing that we try is F, and of course, once we pop off F and notice that it's been visited already, we're going to skip it. So now we do nothing, and then we have D to work with. That's the next thing that we're going to pop off. So now we visit D. So it hasn't been visited, add it, and mark it. And then add all of its adjacent vertices to S. So we've got B, that's the only one. Okay, so we're going to add B to the stack. We're going to push it to the stack, so now B's on top. See what's happening? Okay, so now we have visited B already. We're going to pop it off and do nothing, right? We visited A already. We're going to pop it off and do nothing. We visited A already. We're going to pop it off and do nothing. And then we get back to C. See that? That's the next interesting thing that happens in this stack. We have C at the top now. Okay? So now, oops, go back please. So now we're up here. We have a stack that's still not empty. We pop off the C. We're working with C now. It's not visited. Hey, hey. So we're going to add the C and visit it, mark it. It's the sixth thing that we saw. And then we're going to push all of its adjacent vertices. So we have A and G. That's where we find the G finally. So we're going to push A and G in that order, I guess. And that's how we finally visit G. Cool, huh? So now we're going to pop off the G because we're going to come back around. Hopefully you're following this now. Not too bad, I hope. Pop it off, visit it if we haven't already. Yes, we have. Well, we just did. And so mark it. It is the seventh and final node that we have visited. Add it to the visited set. Push all of its adjacent vertices, which is just C, to the stack. So now we have BAC with C on top of the stack. And, well, we visited all of them. So when we go back to this loop, well, we visited C. We're done. Pop it off. We're not going to do this if statement. All right, we visited A. We're done. Pop it off. We're not going to do the if statement because we visited it. Then B. We're already done with that as well. Now, finally, stack is empty, and we are done with depth first search. And we have visited all the nodes in a weird order, but we got to them all. Okay? And so what this essentially tried to do was make a very long line through all of the, through the graph. Go as deep as possible into it, because we went from A to E to F to B to D like that. That is kind of like the order. Yeah? 1, 2, 3, 4, 5. And then once we got to the end and we couldn't go any more out of D, we then backtracked to somewhere where we could to 6 and 7. Yeah? Hopefully that makes sense. So that is depth first search. And now it's time for a similar one that also visits all the nodes. It's breadth first search. Okay? And I hope you can see why these are all going to like visit everybody. It's going to take this amount of time because you have to push all of your vertices to this queue/stack and push everybody to the stack and then pop them all off, but also push every edge, every vertex along every edge. So you have to like visit every edge and every vertex. So one of the two is a bigger number. If we just go and replace the stack with a queue, the way that we traverse our tree happens differently, okay? This is called breadth first search, and what it does is it likes to start searching wide rather than deep. So it's like, okay, try everybody at this level, try everybody at this level. Yeah, that's the idea, that's the hope. It's like, do this first, then that, then all these. Okay, that's what breadth first search gives you. And so it tries to stick as close to the start as possible for as long as possible. Right? That is different. Seriously, all that is different is change stack to queue. Now you know why we learn about those algorithms, or sorry, those data structures in CSCI 41. And now also I have improved this line. We're not going to push all of these adjacent vertices because sometimes we push ones that we've already visited. We're going to push all of the unvisited adjacent vertices to this time a queue, which is called queue, right? Okay, so, oops. This is now queue. Let us traverse again using breadth first search this time, starting from A. Okay, so my visited stat starts out as empty, and then we have an empty queue. So I've got nothing in it right now. And then I'm going to push our starting vertex, which again is going to be A, to the queue. See that? And now, while the queue is not empty, and it's not, it's got A in it, we're going to pop off the thing at the front, right? Queue's front. Okay? Darn, that's a little too large, isn't it? Let's make it a bit smaller then. There. Okay, we're going to pop off the queue's front and then visit it. Okay, so we're going to visit A right now. We haven't visited it, so we're going to add it. And then we're going to push all of its unvisited vertices, B, C, and E, to the queue. I got popped off. B, C, and E. And now this one's interesting because we're going to then, the next thing that's on the front of the queue that we pop off next is the B. See that? That's how we stay close to where we were. Because then we visit the B, then the C, then the E in that order. Because we always add to the end of a queue, right? So we pop off the B now. Visit the B. Right? And then we push all of its unvisited adjacent vertices to the queue. And notice we've already visited A, so we're not going to touch A anymore. We're going to do D and F. Those are going to be the ones that we push. Okay? So then we are going to visit C, because that's the next thing we pop off of the queue. We haven't visited it yet, so we're going to visit it and push all of its unvisited nodes to the queue. And it's not A, it's just G. Okay? So we'll push G to the queue in that order. And remember that we pop from the front and push to the back in a queue. So then it's time to continue this loop. And we're going to pop off the E. The E is the next thing at the front of the queue. So that's the fourth thing that we visit. So see how we're visiting 1, 2, 3, 4 in level order, essentially. We're sticking close to where we started for as long as possible. And then, so that was E, and then we're going to push all of its unvisited adjacent vertices, so not A, but F, okay? So we're going to push that F to our queue, and there we go. And look how sometimes still we see duplicates. That's okay. That's totally fine. We'll just skip the second F. Okay, so then, coming back, did all this for E. Then we pop off the next thing, which was D. Okay, so we pop off the D. It has not yet been visited, so we visit it. And we push all of its unvisited adjacent vertices to the queue, but there are none. There's only B, and B has already been visited. Okay, back we go. Pop off the F. Okay, we have not yet visited it, so we will. And then, oh, sorry, gotta write the D as well. And we just visited the F, and we're gonna push all of its adjacent vertices to the queue. that have not yet been visited, but we visited B and we visited E, so we don't have to do nothing. And then finally, the final useful thing we do is we visit G. That's the next thing at the front of the queue, and so we pop it off. We have not visited it yet, so we will. And so that's the 7th thing. And then we push all of its unvisited adjacent vertices, which is just C, but we visited it, so we don't have to push it. And then we're done, so that's fine. And then we're going to pop off finally this F, which is a duplicate. And so we have visited it, and so we don't do any of this if statement. And so we go right back to the start. But finally now the queue is empty, so we're done. Done with the whole thing. That is our breadth first search through the queue, or through the graph, using a queue. So see how we stuck close to A. First thing, second thing, third thing, fourth thing, fifth thing, sixth thing, seventh thing. We stayed in like level order. This is distance 0 away, this is distance 1 away, this is distance 2 away. See that? That's beautiful. That's a lot probably easier to think about than this one, which is trying to make a very long path first and then like backtracking to find where it missed other places. Okay, this one's like in level order. Okay, that's breadth first search versus depth first search, and literally the only difference was the choice of data structure, queue versus stack. So that's breadth first search. That's a way to visit every node in a graph and process them. And now I have a fun one for you. It's the most difficult one, but it is very, very exciting and useful. Google Maps, of course, is using this all the time. It's a shortest paths algorithm, okay? What's going to happen is if we take that queue and we replace it with one other data structure that we know, a priority queue, okay, which is secretly a heap, right? That's its underlying data structure representation. If we replace the queue with a priority queue, then we can find the shortest paths in a weighted graph. We can figure out like, okay, the best way to get to from A to like, or the best way to get from like D to, let's say, D to E is not this long route because that's a lot of cost. It is better for you to do this one, right? I think that's 1520 versus 17, right? So that is what this algorithm can prove to you for, and it can find you these shortest paths. So it's named after the man who invented it, Dijkstra, and he is like a legend. He is really, really cool. He was outspoken, and he was just a joy in computer science, okay? We love him. And he, just not to brag, but he just so happens to be related to me in my PhD advisor genealogy. So he was the PhD advisor of my PhD advisor of my PhD advisor of my PhD advisor, so on and so forth. So yeah, this is Dijkstra's shortest path algorithm. And the way that it finds these paths that are short is you give it a starting vertex just as normal, and it's going to go and find the shortest path from that vertex to every other place, okay? It's going to figure out the best way to go that takes the shortest amount of weight to get there, okay? So because we're using a priority queue, we have a different like timing, a different runtime. So it's V plus E, all of that times log of V. So that is the running time of this algorithm that I'm about to show you with a priority queue. But you can actually use a fancier data structure than a priority queue, but that is that's a lesson for an algorithms class that you'll take later, okay? This is still quite nice. It's kind of like sorting speed. Okay, so here's what it is. Don't be afraid. I'm going to give you an example. I'm just going to make it large for you at the very beginning. Let's look at the differences, okay? We keep our visited set. We change our underlying data structure that we're moving things with into a priority queue that can pop things off based on their priority, their numbers, okay? So we're going to make a min priority queue that pops the smallest thing, the minimum of every other thing that's in here, okay? Then we need two other data structures. We need two maps, two hash tables, if you will. And this first one is a distance map. So it takes and gives you the distance to a certain node. So like the distance to A, for example, is a number, and that's what the distance map will tell you about. And then we have a predecessor map. Okay, this one's useful because it tells us how to get to somewhere following the shortest path. Okay, so like the predecessor, if the shortest path was like A, then C, then E, the predecessor of E, we will say is C. Okay, that's what came before it in the shortest path to E. Okay, that's the idea. From a starting vertex to this ending vertex, going backwards. That's what the predecessor map gives you. So with that, we are going to push things. Push to our priority queue the starting vertex, but we're going to make like a big data structure, like a struct, with, yes, the vertex name, but also some information. A previous value, where we came from, and then also a distance value. That's our current guess of the distance to the node. Okay? That is going to make a lot more sense when I give the example, I promise. Okay? And then, essentially, we do all the same stuff. So while the priority queue is not empty, we're going to pop it off and get all of the information out of it. We're going to pop the thing with the minimum distance. That's what our priority queue gives to us. And because we're putting a bunch of things together in like a struct onto the priority queue, we're going to pop them all off. The node, where it came from, and also the distance that we think it has. Okay? And then we're going to do very similar things with the pushing and visiting, but also we need to add to the distance map. We need to add to the predecessor map. Okay? So that was a lot, I know. I'm going to give you an example now, and it should make a whole lot more sense, I promise. Okay, so we're going to run Dijkstra on this graph G over here, and our starting vertex is going to be D. Okay? Our starting vertex will be D. So let's do this. Are you ready? So visited set is empty. Starts out being empty. Distance map starts out being empty. Predecessor map starts out being empty. Our priority queue starts out being empty, and we're going to add to it the starting vertex, which is D, and we're also going to give it like a previous value, and that's going to equal our starting vertex. Like prev is D itself. We're like giving it a little self loop there. Doesn't really matter for the starting one. And then we're also going to say the distance is 0. Okay? So that's our priority queue. And so now we're ready to get started with the while loop. Are you ready? We're going to watch before our eyes how this fancy algorithm comes up with the shortest paths from D to every other vertex in the graph. Okay? So here we go. We're going to pop off this, okay, from the priority queue. We're going to take out the D. D was the previous one, and the distance to this node from D, our start, is 0 because it is the same node. Okay, that's why we put 0 here. It's the same node. That's the distance to it from the start. Okay, we haven't visited it yet, so we're going to add it. We just visited D. Then we're going to save the distance to D. So distance to D is 0. I'm going to say that. The distance of D is equal to 0. And then we're going to set the predecessor of D to whatever it was. We're just going to use D for the start. We're going to say it was its own predecessor. You can say null if you want, whatever you feel like, but that works for us. So, okay. Now, for every adjacent vertex that has not yet been visited, we are going to push these things, okay? We're going to push, it looks like it's just B right now. We're going to push the following. Are you ready? We're going to push that node, so B is what we're looking at right now. That's the next adjacent thing from D. We're going to push B. Its previous was whatever our current V is, where we came from right now, which therefore is D. That's where we came from. And then the distance that we're going to add to this node in the priority queue is whatever the distance to this node that we came from, this current one, plus the weight of this edge. Okay? So it's saying like the distance to this node, our best guess for it is, well, the distance to it from wherever we just started. Okay? So it is 5. 0 plus 5 is 5. Okay? That's how you do it. And so this distance here is our best guess at the actual distance from the start to this node. Okay? It might be replaced eventually, depending on what gets added later. Okay, so now, still, we only have one thing in the priority queue. This guy's gone. Yeah? Back we go. It's not empty, so we're going to pop it off. So we have V being B. Yeah. Then our predecessor, where we came from, was D, and our distance is 5. Okay? So we haven't visited it yet, and so we're guaranteed to know that this is the shortest path to this vertex. Okay? If not, we would have seen something to this vertex before. Okay, so we're going to add it. So we just visited B now. Okay? We just visited B. We're done with it. I'll just circle it to say that we're done with it. And, okay, then the distance to it was whatever we thought it was, 5 from the start. And then the predecessor, where we came from, was wherever our previous value was, which was D. Okay? So the predecessor of B is D in the shortest path. Okay. And then for everybody that hasn't been visited yet from B, so not D, A and F, we're going to add them to the priority queue. Okay? This guy is popped off now. So we're going to add A, and we came from B, and the weight to get from A from B is whatever the weight was from B, which is the 5, plus the 8 more to get to A across from B. Okay, hope you see how that's working. So that's 8 plus 5 is 13. That's one. And then we're going to push F as well, which came from B, and it's 5 plus 3. Okay, our current weight plus 3 is our best guess at the weight. Sorry, that's 8. Is our best guess at the shortest path weight to F. Okay, and this could be overwritten one way or another. Okay, so this is the min thing. This number, this dist, is the min thing that we're ordering our priority queue by, our min priority queue. And so now we're done. Come back, and we're going to pop off the minimum thing, and now we have two choices. We now have to pick this one. Okay, we're popping off F, because we just might find a better way to get to A, going through F, maybe. Who knows? Okay, so we haven't visited F yet, so we're going to add it to our visited set, and we're going to set its distance to be this one. We are guaranteed for it to be the best distance, F8, and then the predecessor of F is where we came from, which is B, which we saved. F maps to B. Then for everybody coming out of F, we're going to push. So B is already taken care of. Let's add the E then, okay, to the priority queue. So E, you can get there from F by, well, taking its 8 and then adding this 9 to cross over. So that's 17. That's our guess at the distance if you came through F. Okay, so then we continue. That's just how it works. Keep on going. Pop the next minimum thing out, which is going to be A in this case. And so it seems that it's not better to go the long way through F to A, because there is a way to get there. No, the algorithm's telling us that, well, the next thing that we need to pop off is A, so that is going to be added. Okay, we know the shortest path to A now. It takes 13. Okay, so that's it. We pop the min thing. We haven't visited the A yet, so we're going to visit it and say that the distance to A is whatever we saved it as, which is 13. And we came here on the shortest path from B. So the predecessor in the shortest path going to A, going to A is B. There. Okay. So yeah, and then we're going to push all of A's adjacent things that we have not looked at yet. And so now we're going to push C and E. See that? So let's push C. C coming from A with distance, 13 plus 7. Okay, hope you see how I'm doing that. That's 20. And then E coming from A. Oh, wait, sorry. That was 13 plus 6 is 19. sorry, for C. Then the E coming from A, its distance is the 13 plus the 7, which is 20. So notice that we have two contenders for the shortest path to E. We're not sure which one to take yet, but the priority queue will tell us. Okay, this is 19. Okay, hopefully this is making some sense. So we just popped that one off. And we just visited A. Okay, so now we have 3 contenders to work with. We need to decide whether or not to visit E, C, or this E from this way. And it looks like the shortest one is this one right here. So going to E through F, okay? Going to E through F. That is the shortest way to get there from the start. Again, it's all relative to the starting vertex. So we're going to pop this one. We just visited E now. We just got there. We knew how to get there. And we're going to say, okay, we haven't visited yet. The distance to E is 17 now. E is 17. The predecessor of E in the shortest path is F. And then we're going to push all of its children if they're unvisited, and they all are visited. So we're good. Coming back. We're going to pop off the next minimum thing, and it looks like it is going to be the C here. Okay, we're going to pop off the C, and that's the shortest path to the C. So, okay, we haven't visited it yet. We see the C, and okay, we're going to save the distance to C. That is what we saved it as. It's 19. We just visited it, and then we have in the predecessor coming to C, we came from A, okay? I'll show you why that's useful. And then we're going to push everything that hasn't been visited from C, and so it's not A, but we're going to push the G here. Okay, so let's push the G to this priority queue. I'm going to say G, and we came from C, and the weight to get to this G from C is G. C's 19 plus G's 1 across that edge, so that's 20. Okay, and so now we have two 20s sitting in the priority queue, and we can pop any one of them. It doesn't matter which. So let's just pop this one, pop the E, and so we actually already visited E, so this is definitely not a better shortest path. So we're good, we can skip it. Then we come back and we pop this one. And this one hasn't been visited yet. This is for G. We have not yet visited G yet. Okay, so we're going to add it to our visited set. And okay, then we're ready. The distance to G, we are confident the shortest path from D is 20. And its predecessor, where we came from along the shortest path, was the C that we saved. Okay, hopefully this is starting to slowly make sense, and we push everything that hasn't been visited, but we visited everything now, so we're good. Okay, and so the while loop is finally over with. The priority queue is empty. And here's what we built up. Our visited set, our distance map, and our predecessor map. So the distance map tells us the shortest path from our starting vertex, which was D, to everybody else. So the shortest path from D to D is, of course, 0. The shortest path from D to F is 8, okay? You go like that. You don't go like this, yeah? See how it's working, slowly but surely? And let me use the F as the example, okay? So let's pretend we wanted to know the shortest path to F in this graph. And so we know that the distance is 8. The shortest distance to F is 8. Let me draw that example. It's like this. But how do we know the path itself? That's where the distance map comes into play. The predecessor map. And then what you do is you start at where you wanted to go to. So you start at the F, and then you follow the distance map. So the predecessor in the shortest path from F is B. So we came from B. See that? And then we go look at B in the predecessor map. The shortest path from B comes to D, okay? And then we can just remember that D was our starting vertex, and we can stop our search there. And so the shortest path of length 8 is this right here, DBF. And you can read it off backwards from the predecessor map. Okay? I know this is weird, this is a lot, but it's a very, very important algorithm that I want you to have seen at least once before you study it again in your algorithms class later on in your computer science career. So that is the Dijkstra shortest paths algorithm. Okay? It's all this bunch of code, and hopefully going through this example is giving you a feeling for why it's working. Okay? It's always saving up its best guess of the shortest path to a certain place, to a certain node from the start. And the way that the priority queue works is that it will always consider the minimum thing next. And so the minimum one is always going to be the shortest path to that node. Okay? Which is why when you have two things, like you can try to get to E through F or through A, we always pick the minimum one first, so we don't ever take the long route. Okay? That's kind of the hand-wavy proof as to why it works. But that, in a nutshell, is graph traversal, graph shortest paths algorithms, and graphs in total. So that is all I have to say to you about graphs for now. We'll study them a little bit more in the trees chapter, but I think that's plenty for a start. So thank you for getting through the graphs with me, and I will see you later.